Interesting about this one coming up is you can only use the antiderivative for certain regions because the antiderivative has asymptotes in areas where we would need to do a calculation, like here at pi. But fortunately, if you look closely at this graph, you can see 1, 2, 3, 4, 5, 6, 7, 8 zones. So you just have to figure out 1 and multiply it by 8. And that's allowed because these graphs, sine curves, are uniform. In other words, they don't suddenly go up and down, bigger and change. And this graph here is a secant tan. So the secret is knowing what would the oh boy oh boy what is the antiderivative of those? Let's see if I got it before the screen came up. No, I didn't. Of course not. I don't want to ask AI assistant. So the secret is what's the antiderivative of these particular functions? And that's the hard part. That's really what they're testing you on. And they're also testing you on if you know how to take um, an integral. So again, the area under this graph, this red line, goes all the way down here, and the area to this blue graph goes all the way down there. If you to take this area, subtract this area, you get the area of interest. So it means we have to take 2 sine x. We take the integral of 2 sine x minus a half secant tan x. Great for a calculator to do, but not great for figuring it out in your head or by hand. So one thing we also should do here, because this is a particularly this one, is look up the exact trig values and just keep it handy. And always learn how to figure out your exact trig values. And you should have one in radians, by the way, because at this level it's supposed to be in radians, so we can use that one. And they also tend to have the root at the top. So how do we figure out what's the antiderivative of that? Well, that takes knowing what the derivatives are. So another thing you should sort of memorize are the key derivatives, or I guess it's called the parent derivatives of 6 trig functions. And there we go. Right there, we'll use the one on the left. So you should also be familiar with this. Now, the nice thing is, none of these have a double angle inside. They're all x here, and x here. 2x would require taking the derivative of the angle in here as well. But these angles in here have not been transformed, which means this is just a multiplier. In other words, ignore the 2 for now and ignore that for now and figure out what is the antiderivative of that. Well, we can see it right there. The antiderivative of that is secant x, which means the derivative of half secant x is equal to that function. And then we can look for the sign right here, negative sign. So that means if I had negative cos and took the derivative of it, I would get positive sine. If I take positive cos and take the derivative, I get negative sine. But this is a positive sign. So I have to take the negative 1 times the derivative of the cos, and I will get that. But there's a 2 here, so I have to take negative 2. So that means the antiderivative of this one is minus 2 cos x. You can prove this easily in Desmos. But here's the problem. The secant at this point, if I'm going to use these to solve the area, the secant at this point is an asymptote. So if I was to use this for this area, and then again, I think for 2 pi, I will not get an answer. So I can only use them for specific areas, and the area we're going to focus on is there, which is why your teacher highlighted that area. So that means you would have 2 ways to do this. So I'm going to just copy our antiderivatives. Actually, I'm going to copy everything to the right. There we go. That's exactly what I wanted. Now we also have to figure the x values. But it's clear that this goes from 0 to pi over 3. Be careful. In this case, the 0, 0 is a 0 area underneath, but not so for the antiderivatives. Did I just screw up my It doesn't matter. I screwed up my antiderivatives. I'll just write them again. This is my first antiderivative, and this is my second antiderivative. Not so for these, because a cos x curve at 0 starts up here and goes down. The negative version starts down here and goes up. So be it -2. So that means I have to beware that 0 here does not have a 0 answer. So I have two methods I can use. I can take the integral and my calculator from 0 to pi over 3 of the original functions they gave me from this space here, which is the upper graph. You always take the upper graph as the first one, minus the second graph. So this is what we're solving. Times the difference in x, times the difference. So it's multiplying every value through there. So we have usually a little dx here. So it's 2 sine x minus that will give me the area in an integral. Or I can use this and say from 0 to pi over 3, I'm going to take minus cos x of pi over 3, and I'm going to subtract this here, half a sine secant x. I'm just going to put these up here where they're safe, minus this. And I have to do for pi over 3 there, for there. I have to do this one. So it has to be for pi over 3 here and pi over 3 here. And I have to solve that. Now, fortunately, there's some exact values. Not the one doesn't matter. And then I have to subtract, open brackets, the subtraction of this for 0. Minus this function for 0. I don't need these anymore. But you should know basically the derivatives of all these functions. I don't know if your teacher expects you to memorize it or not. And then for this value over here is going to be for 0 and 0. Well, fortunately, I have all the values on the table up here. So cos of pi over 3 is right there. It's a half. I'm going to multiply it by -2. It becomes -1. Then the secant of pi over 3 is going to be the flip of whatever the cosine of pi over 3. Secant is the inverse of cosine. So the cosine of pi over 3, as we just discovered, was a half. So the secant is the inverse of that, 2. And it's going to be multiplied by 1. So -1. So I get minus, and -1 because it was multiplied by -2. And then minus a half times 2 minus 1. So I get -2. And then be careful here. This minus here is separate from this minus. So now the cos of 0 degrees is here, is 1. And -2 of that times 1 is -2. And then the secant of 0 degrees is the inverse of that. The inverse of 1 is 1. So I get -2 minus half of 1.5, which is -2.5. So this bracket on the left becomes -2. And then minus, this bracket on the right became minus 2.5. But we have a minus minus situation. So it becomes minus 2 plus 2.5, which becomes 0.5, which means the area in this graph right here is 0.5. And there's 8 of them. So the total area, 8 times 0.5, 4 is the answer. You can easily prove this all using your secant, or using your Desmos. You can do it both ways. We can make the graph of the original graphs. G of x is equal to the half secant x tan x. And you can ask Desmos to solve it from the top function to the bottom function. And you have to put a dx there. And it tells me the answer, 0.5. And that's just for this region right here, right there, that area right there, 0.5. But you can also take the functions we did. We'll call them h of x, negative 2 cos x, and I of x, half secant x. And you could prove to yourselves that they're the right choices. We'll just turn off these. And we'll just turn those off by taking the derivative of them. So I'm going to take the derivative of negative 2 cos x here, the derivative of hx, and see if it matches my 2 sine x. It does. And then I can take the derivative of the I function, half of secant x, to see if it matches my g function. Yes, it does. Therefore, these are the correct derivatives of my functions. So you have to do h of pi over 3 minus I of pi over 3 minus 2, as we calculated, minus h of 0 minus I of 0. And the total is 0.5. And you can see the right is indeed 2.5. Well, the minus of the right would indeed be 2.5. There you go. So therefore, it's good. Now, here's why you can't use it for pi to, or 3 pi over 2 to pi, which is this area right here. The next area, you see, it goes from 2/3 pi to pi. Well, that's because h of 2/3 pi exists, and I of 2/3 pi exists, but h of pi exists, but I of, oh, that shouldn't have worked. Let's see if we get the same answer. And the reason I say it shouldn't have worked is because if we look here, see, oh yeah, no, should have been fine. Okay, yeah, it should work fine. Let's see if it can add it all the way up. Well, you'd have to do it individually over and over again. It might be able to work for this one if we go all the way from 2 pi and minus 2 pi. But it's going to hit some undefined because there's some asymptotes. Yeah, it's saying 0 because some of them are under the graph, and when you have under the graph, it's 0. Well, that's a good point, actually. When your teacher asks this, is he asking you to consider the bottom spaces negative? Because in integral calculus, yeah, the difference between the space has a volume, but the actual integral underneath is a negative. So technically, all these would come out as 0. So maybe it's a trick question, right? If it says 0, then it's a trick question. Then they're actually counting the integrals at below as negative, which is the normal way. For instance, if I take this value here, it goes from 0 to there, which is this value here, negative pi thirds. Let's see what it says. Yeah, you see, things below the x-axis are negative space. So this might be a trick question and the answer might be 0. And they didn't expect it. I don't think so, though, because of all the detail that's in this. I think he's counting that as volume. Yeah, he's just counting his total area as opposed to the actual integral. The actual integral answer to anything below the x value, x-axis, is negative. Anyway, moving on. That wasn't that bad.